Welcome to the Volume Graphics Tutorials. In this video, I will guide you through the workflow of a P203 porosity analysis in BDG Studio Max. The P203 porosity analysis is based on the German BDG reference sheet P203. This guideline was originally designed for CT evaluation of light metal castings, but can be used as a reliable evaluation method for a variety of applications. The casting sample I will use to demonstrate the workflow is a pump bracket raw part. It is a typical die-cast workpiece made of an aluminum silicon alloy, which was produced in large quantities for the automotive industry. It is an ideal example to demonstrate a P203 porosity analysis. It offers the wall thicknesses of 3 to 5 millimeters that are common for the die-casting primary molding process. And it also offers some larger material accumulations with wall thicknesses greater than 6 millimeters, which can lead to a higher probability of porosity in the die casting process. In this video tutorial, I will examine and tolerance the complete casting with a global porosity key. And I will examine and tolerance 4 functional and strength-relevant test regions on the pump bracket: a hollow cylinder below the sliding surface, another hollow cylinder below the sealing surface, and 2 half-shell-shaped bodies below the sliding bearing surfaces. The test regions were previously created in BDG Studio Max based on the 3D CAD model of the final part and saved in a template that I will import into my project. The workflow I will show you in this video will include the following steps: loading the VGL file, performing a surface determination on the volume object,
importing the CAD model and aligning the volume object against the CAD model,
importing the test regions, setting up and performing the P203 porosity analysis, and finally, evaluating both the casting and each of the 4 test regions with the help of porosity keys that I will create in BDG Studio Max. As an extra, I will show you at the end of this video how you can save a porosity analysis for its later use in an automated process. Okay then, let's get started. I'll open BDG Studio Max and, on the Welcome page, select the Porosity tab. This way, I have all important controls for porosity analysis conveniently in one place. To load the VGL file into the scene, I'll select File, Open, and Browse for the VGL file. The volume data will be loaded into the scene. To visualize the further workflow steps, I will make the volume object transparent. I'll go to the Rendering tool, and I'll set transparency to 65%. Next, I will perform a surface determination. The volume object is composed of millions of small voxels with different gray values. Before I can perform the porosity analysis, I need to give the volume object a functional surface. On the Home tab, I'll select Surface Determination Advanced Classic. The Surface Determination dialog will open. All I have to do here is activate both Filter Particles and Filter Voids options to make sure that pores and particles won't get their own surface. And for the Filter Voids option, I will change the setting from Remove Small Voids to Remove All Voids. And that's it. I'll click Finish to start the calculation. The volume object now has a valid surface determination, which is indicated by the red icon here in the scene tree. As a next step, I will align the volume object against the CAD model. This alignment is necessary because the test regions that I will later import into my project were created on the CAD model. So, I have to make sure that the test regions will be placed exactly where they belong on the volume object. Let's start by importing the CAD model. I'll select Quick Import and browse for the CAD file. In the CAD Import dialog, I can select the mesh accuracy. In our case, a medium mesh accuracy will suffice, so I'll click Import, and the CAD model will be imported into the scene. Now I can perform the alignment. In the scene tree, I'll select the volume. Then, on the Home tab, I'll select Alignment and Best Fit Alignment. I'll check that the volume object is the object to be aligned, and the CAD model is the reference object. Then I'll click Finish to start the calculation. The volume object has now been aligned to the CAD model. From here on, I will only be working with the volume object. So, I can make the CAD model invisible by unchecking the checkbox in front of CAD 1 in the scene tree. That's done. Now, as a next step, I will import the test regions. In the scene tree, I'll right-click Volume 1, select Import, ROI Templates, and browse for the ROI template that contains the test regions. In the Import dialog, I need to make sure that all test regions are selected. Then I can click Import. Now my 3D window shows the pump bracket with the 4 test regions. We have colored the test regions to make them visible. If we want to see the test status colors of the test regions later when looking at the analysis results, we need to switch the rendering of the test regions off, so let's do that. Okay, let's hang on a second and take a look at our workflow. We have performed a surface determination, we have aligned the volume object against the CAD model, and we have imported the test regions. As a next step, we will set up the porosity analysis. In the scene tree, I'll select the volume object. On the Home tab, I'll select P203 to open the Properties dialog of the analysis. Now, what you see here is the Settings tab of the analysis. At first sight, this tab might seem overwhelming, but actually, there's not much to do here. So let's take a second and focus on what's important for you. Let's start with the analysis parameters. By default, the P203 porosity analysis is based on the VG Isopor algorithm. This algorithm comes with a set of default parameter values, which allow you to quickly achieve meaningful analysis results for a lot of everyday use cases. But of course, the tab offers extensive setting options, which, if necessary, enable experienced users to individually optimize the analysis parameters. Why is that necessary? Well, scan parameters, complex workpiece geometries, different wall thicknesses, and different material densities are some of the factors that might make it difficult to obtain all relevant indications with the default settings. Anyway, in the case of the compact pump bracket made of cast aluminum alloy, I can work with the default values. Okay, what's next? The quality factor in the scan quality section allows you to see if the quality of your scan is sufficient for the analysis. A quality factor below 3 could indicate inadequate image quality, which might result in poor analysis results. For the pump bracket scan, the quality factor looks fine. So let's move on to the visualization settings.
In the active column section here, I can select the parameter I want to have visualized color-coded in the analysis results.
By default, this is volume. Since I am interested in the diameter of the pores, I will change this setting here to diameter. Now the analysis result will be visualized color-coded according to the diameter of the detected indications. And there is one last thing I would like to show you. I can filter out pores I don't want to have in my analysis results. I am not interested in the pores with a diameter below 0.5 millimeters, and I would rather not have them listed or displayed in my analysis results. So let's filter them out. In the Filter Result option, I'll set minimum size here to diameter, and enter the value 0.5 millimeters in this field here. This means that all pores with a diameter below 0.5 millimeters will not show up in the analysis results. And that's it for the settings. I'll click Calculate to start the analysis. Once the porosity analysis has been completed, the status bar in the Properties dialog will change from yellow to green. I will close the Properties dialog for now to take a look at the color-coded visualization of the analysis results in the 2D views and the 3D view. The detected porosities are visualized color-coded according to their diameter. In the 2D views, I can see the outline of the detected indications. Okay, we have performed the porosity analysis. It's time to create the porosity keys. Before we see how this is done in the software, let's take a closer look at what porosity keys are. The porosity key is a set of parameters, specified by the customer, that define a permissible porosity, either for a complete structural part or for a specific test region on that part. This porosity key here specifies the porosity parameter for the test region at the bearing surface of the pump bracket. According to this porosity key, the test region must comply with the following conditions. The pore volume fraction, that is, the total porosity, does not exceed 0.05%. The maximum number of pores is 5. The maximum permitted diameter of a single pore does not exceed 1.5 millimeters. The sphericity of the permitted individual pores is at least 0.5. The minimum distance between two adjacent individual pores is 5 millimeters. And finally, Pores with a diameter of less than or equal to 0.5 millimeters are not taken into account. Now we need to get this information into our software. Let's see how this is done. In the scene tree, I'll double-click the analysis to reopen the properties dialog. I'll go to the P203 keys tab. Here, I'll click the Add Key button at the bottom of the dialog. Let's recall. For the pump bracket, I want to create 5 keys. A global porosity key for the entire casting, and a porosity key for each of the 4 local test regions. Let's start with the global key. In the Add Key dialog, global key is selected by default, so I can directly enter the porosity parameters. Global porosity, less than or equal to 0.1%. Pore diameter, less than or equal to 3 millimeters. According to the customer specification, I will exclude porosities with a diameter of less than or equal to 0.8 millimeters from the porosity analysis. And that's it. As you can see in the resulting key field, BDG Studio Max immediately generates the porosity key. I'll click OK, and a first table entry will be created. Now let's take a closer look at this table. The P203 keys table allows me to immediately evaluate the porosity analysis. The porosity key here in the first column is highlighted in red. This means that at least one of the porosity parameters did not meet the porosity specification. The value in the out of tolerance values column, also highlighted in red, shows me which porosity parameters are affected. In our case, the parameter that does not meet the specification is the pore diameter. The largest deviation is 11.22 millimeters. The value 9 in square brackets tells me that a total of 9 indications exceed the permissible diameter up to 3 millimeters. The porosity parameter for total porosity is also displayed and highlighted in green, which means that the porosities analyzed in the casting comply with the customer specification in terms of total porosity. If I want to find out more about the indications that exceed the permissible pore diameter, I can switch to the Indications tab. In this table here, I can sort the pore diameter in descending order by clicking the column header twice. I have created the global porosity key. Let's move on to the porosity keys for the local test regions. We'll start with the first test region at the sliding surface of the pump bracket. Back on the P203 Keys tab, I'll click the Add Key button. This time, I'll select Freeform ROI key. Then I'll select the first test region. Now I can enter the parameters for the porosity key. Local porosity less than or equal to 0.05%. Maximum number of pores, 5. Pore diameter, less than or equal to 1.5 millimeters. Sphericity greater than or equal to 0.5. Minimum gap between pores, 5 millimeters. And pores with a diameter of 0.5 millimeters or less will not be taken into account. Again, I can see the porosity key in the resulting key field. I'll click OK, and another table entry will be added to the table. This time, all values for the individual porosity parameters are highlighted in green. This means that the porosity specification for the test region at the sliding surface of the pump bracket is met. Let's move on to the next test region, which is the one at the sealing surface of the pump bracket.
I'll click the Add Key button.
I'll select Freeform ROI key and the second test region. Now let's hang on a second. I could enter the porosity parameters one by one, just as I did before. But since the porosity parameters for the second test region are identical to those of the first one, I can save myself quite some typing. When I click the Recent Keys button at the bottom of the dialog, I can select the key I last created. As you can see, the new key is generated immediately. I'll click OK, and the new porosity key will be added to my table. All porosity parameters are green, which means that the porosity specification for the second test region is also met. As you can see, creating porosity keys is intuitive and done with just a few clicks. Let's go on with the porosity keys for the test regions at the sliding bearing surfaces of the pump bracket. Again, I'll click the Add Key button. I'll select Freeform ROI key and the third test region. Then I'll enter the specifications. Local porosity less than or equal to 0.15%. Pore diameter less than or equal to 0.6 millimeters. Sphericity greater than or equal to 0.3. I'll click OK to add the new porosity key to my table. Look here. The porosity key is highlighted in red. The porosity specification is not met. There is one pore that exceeds the allowable diameter. For the test region at the second sliding bearing surface, I can again use the Recent Keys function. I'll click Add Key, select Freeform ROI key, and the fourth test region. Then I'll click the Recent Keys button and select the key I created for the test region at the first sliding bearing surface. I'll click OK to add the fourth and final local porosity key to my table. This time, the porosity key is highlighted in green. This test region again complies with the porosity specification. I have created all 5 porosity keys, a global porosity key for the entire pump bracket and one porosity key for each of the 4 test regions. And the P203 keys table here gives me a really nice overview of the analysis results. Let's close the dialog and again take a look at our analysis results in 2D and 3D.
In the 3D window, you can see the result of the porosity analysis nice and clearly.
Thanks to the color-coded visualization, the detected porosities can be distinguished from each other quickly and clearly. The 4 local test regions are highlighted in green or red, according to their test status. For each of them, there is an annotation that indicates the porosity key, the results for the individual porosity parameters, and the test status. While 3 of our test regions comply with the porosity specification, 1 test region does not. Plus, the pump bracket does not comply with the customer specification for global porosity. At least 1 larger shrinkage hole-like porosity was detected, which violates the global porosity key. This is indicated by the out-of-tolerance pore annotation here. And last but not least, in the 2D views, only the outline of the detected porosities is colored, which allows foundry specialists to gain insightful insights into the detected porosities. We have come to the end of the workflow for an example P203 porosity analysis in BDG Studio Max. To round this tutorial up, let me show you how you can save a porosity analysis to use it for an automated workflow. This will come in handy for repeated porosity analysis on other castings of the same type, for example as part of an initial casting sampling, or for series accompanying sample tests in ongoing production. For an automated process, you need to set up and perform the porosity analysis once, and save it in what we call an evaluation template. Since I have an analysis at hand, let me show you how this is done. Once I have run my analysis, I'll right-click the volume in the scene tree and select Export Evaluations. Then I can give my evaluation template a name and save it. In an automated porosity analysis workflow in BDG Studio Max, I can record the import of the evaluation template with a macro and then use it as often as I want. And that's it. In this video, I have guided you through the complete workflow of a P203 porosity analysis in BDG Studio Max. This analysis is performed in accordance with the BDG reference sheet P203 and allows for consistent and replicable evaluation of castings. You can inspect not only the entire component, but also functionally relevant areas of a component by defining and tolerancing test regions. And creating porosity keys in BDG Studio Max is as easy as copying the information from the technical drawing. This was the first of our 3 tutorials on P203 porosity analysis in BDG Studio Max. If you want to dive deeper into the topic, make sure to check out these tutorials. In our tutorial, P203, Automating a Porosity Analysis Workflow, you'll learn how to automate the workflow we've set up in this tutorial. Remember that we have imported the test regions by means of a template. Well, in our tutorial, P203, Creating Test Regions Using CAD Data, you'll learn how to create the test regions on your own. And, of course, you'll find the PDF version of this video tutorial if you want to try it out on your own. I hope you enjoyed this video. You'll find a list of all our tutorials on our documentation landing page via Help, Show Tutorials. Plus, make sure to register on Nexus and make it your go-to place for sharpening your expertise. Get access to this video and other information material to get the best out of our software. And visit the BDG community. to exchange ideas, ask questions, and discuss topics with other users and our Hexagon experts. And stay up to date on the latest news and developments. Register now, a world of insight await. Thanks for watching, and see you soon on Nexus.